Question 2 then revolves around this compound, and part A asks for actually quite a lot of information because it wants a name and a molecular formula and the values of these two bond angles. So make sure you read the question carefully and give all the things that it asks for. So if we do the name first of all, it's going to be very difficult to base that name on benzene as the root, because if, for example, we made this ring the benzene that was the root name, then the whole of this would have to be named as a branch, and that's going to be really hard to do. So what you have to do is think of naming these benzene rings as branches themselves and make the root this chain through here. So if we look for the longest continuous chain, we can see we've got this. If we just highlight it in green there. Okay, so we've got a chain of 4 there, which is our longest continuous chain, excluding the benzene rings there. So to name that, that's going to be bute, which remember tells you the 4 carbons, and it's going to be ene because of the CC double bond. And I've left a gap there because we need a number to indicate where in the chain of 4 the double bond comes. So we've got to decide which end to start numbering, and remember, because that's the going to be the ending of our name, it's going to be something 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 butene, that number needs to be as small as possible. That one gets priority in making the numbers as small as possible, and therefore it's going to be numbered like this: 1, 2, 3, 4, because then this becomes but1ene is the root name. And then we've just got to recognize that it's got 2 benzene rings attached, both of them attached to carbon 1, and so it's 1,1-diphenyl. Okay, so you've hopefully picked up this term phenyl, which is what you call a benzene ring when it's a branch, when it's attached to something else in the molecule. So 1,1-diphenyl, because each of the benzene rings needs a number, so 1,1, and diphenyl to make it clear that there's 2 of them. And then carbon 2 has a methyl group attached, so it's 2-methyl. But1ene is the name. Now to get the molecular formula, again you can just go through and count them all, but it is worth getting used to the fact that when you have a phenyl group like that, that's a C6H5 group. So a quicker way to do it would be to say, right, well, we've got 2 of those, so if we just take those 2 together, that's C12H10, and then just count the rest of it. So we've got 13, 14, 15, 16, 17 H, and then we've got the 10 there, and then 11, 12, 13, 14, 15, 16, 17, 18 is the molecular formula. And then the angles. So you've got to get practiced at using these ideas about shapes of molecules and bond angles from the stuff we did in the first term and applying them to organic compounds. So that angle A is basically equivalent to saying, what's the shape around that carbon there? And if you think about it, that's like an alkene carbon, right? So when we were talking about shapes, we said, right, if you have a carbon like this with a double bond around it, it has 3 areas of electron density repelling each other, no lone pairs, just 2 bonds and a double bond, and equal repulsion means that you'll get a trigonal planar shape, and therefore the bond angle is 120 degrees. And it's the same when you have a benzene ring, that the fact that the pi electrons here are delocalized rather than localized in the double bond is neither here nor there. It's still just 3 regions of electron density around there. So the answer is going to be that that is 120 degrees to trigonal planar structure. The other way to think about that would be as just as a geometric problem, and realize that the angle there inside a hexagon is 120 degrees, and just for the symmetry those 2 must be the same, so each of them must be 120. You could figure it out that way, but easiest thing is remembering the stuff from the first term about shapes of molecules. So for this carbon, you can see that it has 4 regions of electron density because it's got a bond to this carbon, it's got a bond to that one, and it's got 2 bonds to hydrogen. So that one is going to be tetrahedral because you're going to have CH3 and H and H and the rest of the molecule, which is this. Okay, so this carbon here is going to be like that because it's got 4 separate single bonds around it to the methyl group, the 2 hydrogens, and the rest of the molecule like that. So it's tetrahedral, which is what you get when you have 4 regions of electron density around a carbon, and the bond angle for that is 109.5 degrees. So that is the answer to the question. Part B then wants to know the total number of pi electrons in that molecule. So what you have to remember is that when you have a benzene ring, there are 6 pi electrons. Each of the carbons has 1 electron in that p orbital. Remember, the p orbitals are all lined up side by side. Each of those contains 1 pi electron. So the delocalized ring that's formed will have 6 in it. So you'll have 6 from there, and 6 from there is 12 so far. But remember, you've got an alkene group as well. And an alkene group has a localized pi bond, which is a shared pair of electrons in one of those pi bonding orbitals. So that's 2 more electrons. So 6 plus 6 plus 2 gives you 14 pi electrons altogether, is the answer. C then is asking what happens when this reacts with aqueous bromine in the dark. So this is where we started with aromatic chemistry. This is where we first noticed that there is something weird about benzene rings, which was that they do not react with aqueous bromine in the dark. So if you've put in any reaction involving the benzene rings, you've got to think, hang on a minute, I should have slowed down, I should have thought, what's the big thing we learnt that introduced the whole idea that there's something strange about aromatic compounds? They fail to react with aqueous bromine unless there's a catalyst there, and there's no catalyst mentioned, so there isn't one there. But this is an alkene group, and that of course can react with aqueous bromine in the dark because it can do an addition reaction. So all that happens, if you remember that reaction, is in effect that the bromine adds across the double bond like that. So 1Br to that end, 1Br to that end. So you just get that plus bromine will give you, all of this molecule will still be there because this is an addition reaction. You're not losing any of the existing atoms from the molecule. The only thing you're losing is the pi bond because that's breaking open, and so we now only have a single bond between those 2 carbons in the middle there, and instead we now have 1 bromine here and 1 bromine there. Okay, so it's the classic alkene reaction, addition across a double bond. And then in part 2 it asks what type of mechanism is that addition, and it's electrophilic addition. Remember, that's the thing with these carbon-carbon double bonds, that the pi electrons are easily accessible to something which is good at grabbing an electron pair, which is what we call an electrophile. And so alkenes react by electrophilic addition. Aromatic compounds, when they do react by electrophilic substitution. But for this one, it's addition, because it's only the alkene that reacts.